Let's start unraveling the mysteries of our galactic home with our first incredible fact. The Milky Way is ancient beyond imagination, yet it's still growing. Our galaxy began forming over 13 billion years ago, making it nearly as old as the universe itself. But here's what makes this truly fascinating. While most things in nature reach maturity and then remain stable, the Milky Way continues to evolve, absorb smaller galaxies, and literally grow larger with each passing million years. Right now, as you're listening to this, our galaxy is slowly consuming at least two smaller companion galaxies, gradually incorporating their stars into its own magnificent spiral structure. The galaxy rotates, but not like a solid wheel. If you could watch the Milky Way from above over millions of years, you'd see something that might surprise you. The inner regions spin faster than the outer edges, creating a differential rotation that continuously reshapes those beautiful spiral arms we see in photographs. Our solar system, located in one of these spiral arms, completes one full orbit around the galactic center every 225 million years. Think about that for a moment. The last time Earth was in this exact position relative to the galaxy, dinosaurs were just beginning to dominate the planet. We live in a cosmic traffic jam, and it's actually protecting us. Those spiral arms aren't just beautiful patterns in space. They're regions where stars, gas, and dust get compressed together, triggering intense bursts of star formation. These areas are also filled with massive, short-lived stars that explode as supernovas, flooding their surroundings with deadly radiation. Fortunately, our solar system orbits at just the right speed to avoid spending too much time in these dangerous neighborhoods. We drift in and out of the spiral arms, but never linger long enough to face the full fury of their stellar fireworks. The center of our galaxy harbors a monster that defies comprehension. Deep in the heart of the Milky Way lurks a supermassive black hole called Sagittarius, a star. This cosmic behemoth contains the mass of over 4 million suns, yet it's compressed into a region smaller than our solar system. We can't see it directly because black holes trap even light itself, but we can watch nearby stars whipping around it at incredible speeds, some reaching thousands of kilometers per second as they dance on the edge of oblivion. Our galaxy has survived multiple cosmic collisions and bears the scars. The Milky Way didn't form in isolation. Over billions of years, it has cannibalized dozens of smaller galaxies, and we can still see the evidence of this violent history. Streams of stars stretch across our sky like ghostly ribbons, marking the remains of galaxies that were torn apart by our galaxy's immense gravity. Some of these stellar streams wrap around the Milky Way multiple times, creating a complex web of ancient destruction that tells the story of cosmic evolution. Dark matter outweighs everything we can see by a factor of 10 to 1. Here's something that will keep you awake at night, pondering. All the stars, planets, gas, and dust that we can observe in the Milky Way represent less than 15% of its total mass. The rest consists of something called dark matter, a mysterious substance that we can't see, touch, or detect directly. We only know it exists because without it, galaxies like ours would fly apart. The gravity from all the visible matter simply isn't strong enough to hold everything together at the speeds we observe. Stars in our galaxy come in an incredible variety that spans the entire spectrum of possibility. The most massive stars in the Milky Way burn with the intensity of millions of suns, but live fast and die young, surviving only a few million years before exploding catastrophically. At the other extreme, the smallest red dwarf stars burn so slowly and efficiently that they could theoretically shine for trillions of years, far longer than the current age of the universe. Between these extremes lies every possible variation, from stars hot enough to ionize the space around them to cool stars barely warmer than a kitchen oven. The galaxy produces about 7 new stars every year, but this rate is slowing down. Star formation in the Milky Way peaked billions of years ago when the galaxy was younger and contained more of the raw materials needed to build new stars. Today, the process continues, but at a much more leisurely pace. Each new star represents a complex dance of gravity, pressure, and nuclear physics that transforms cold clouds of gas and dust into blazing nuclear furnaces that can shine for billions of years. We can only see a tiny fraction of our own galaxy from Earth. Despite living inside the Milky Way, our view of it is severely limited. Vast clouds of interstellar dust block our vision in many directions, particularly toward the galactic center. It's like trying to understand the layout of a vast forest while standing in the middle of it during a thick fog. Astronomers have had to use radio waves, infrared light, and other invisible forms of radiation to map the true structure of our cosmic home. The Milky Way is racing through space at an incredible speed, carrying us along for the ride. Our entire galaxy is moving through the universe at over 600 kilometers per second, relative to the cosmic microwave background radiation. That means as you sit there listening to this, you're traveling through space at more than 2 million kilometers per hour. Yet because everything around us moves together, we feel perfectly still, like passengers on a cosmic cruise ship sailing through the sea of space. Magnetic fields thread through the entire galaxy like invisible highways. The Milky Way is permeated by magnetic fields that stretch across thousands of light years, channeling the flow of charged particles and influencing everything from star formation to the paths taken by cosmic rays. These fields are incredibly weak by Earth standards, but their sheer scale makes them powerful shapers of galactic evolution. They act like invisible infrastructure, guiding the movement of gas and dust that will eventually become new stars and planets. Some regions of our galaxy experience violent storms that dwarf anything on Earth. Near the galactic center, where stars are packed much more densely than in our neighborhood, gravitational interactions can fling stars out of the galaxy entirely, at speeds exceeding 1,000 kilometers per second. These hypervelocity stars become cosmic refugees, doomed to wander the space between galaxies for eternity. Meanwhile, other regions experience stellar winds so powerful they can strip entire solar systems of their atmospheres. The Milky Way contains structures older than most other galaxies in the universe. Globular clusters, dense balls of ancient stars that orbit our galaxy like distant moons, contain some of the oldest stars known to exist. These stellar time capsules formed when the universe was just a fraction of its current age, and they've remained virtually unchanged for over 10 billion years. Studying them is like examining fossils. except these fossils are still burning brightly in the night sky. Our galaxy is surrounded by a vast halo of mystery. Extending far of the beyond the visible disk Milky Way is an enormous spherical halo filled with dark matter, ancient stars, and the remnants of destroyed galaxies. This halo is so large that it may extend halfway to the Andromeda Galaxy, our nearest major galactic neighbor. Within this halo, dozens of small satellite galaxies orbit like moths around a flame, gradually being pulled apart by the Milky Way's immense gravitational field. The chemistry of our galaxy tells a story of stellar death and rebirth. Every element heavier than hydrogen and helium was forged inside the nuclear furnaces of stars or created in the violent explosions that mark their deaths. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were created by stars that lived and died billions of years ago. In a very real sense, we are made of recycled stardust, our bodies composed of atoms that have journeyed across the galaxy for eons before becoming part of us. Time moves differently in various parts of our galaxy due to the effects of gravity and motion. Einstein's theory of relativity tells us that time is not absolute but depends on gravity and velocity. Near the supermassive black hole at our galaxy's center, time passes more slowly than it does here on Earth. The difference is tiny, but measurable. Meanwhile, stars racing around the galactic center at high speeds experience time dilation effects that would be noticeable if we could somehow observe them closely. The Milky Way is part of a larger cosmic dance involving dozens of other galaxies. Our galaxy belongs to what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity. The two largest members, the Milky Way and Andromeda, dominate this group and are slowly approaching each other for an eventual collision that will occur in about 4 billion years. When that happens, the night sky will be transformed as the two galaxies merge into something entirely new. These are just the beginning glimpses into the incredible complexity and beauty of our galactic home. As we continue this journey together, we'll explore even more fascinating aspects of the Milky Way, from the bizarre physics of neutron stars to the possibility that our galaxy might be teeming with worlds that could harbor life. Each fact builds upon the last, creating a picture of our cosmic neighborhood that is far stranger and more wonderful than our ancestors could have ever imagined. Stellar nurseries within our galaxy are cosmic cathedrals where new worlds are born. Scattered throughout the Milky Way are vast molecular clouds, some spanning hundreds of light years across, where the temperature hovers just a few degrees above absolute zero. These frigid regions might seem lifeless, but they're actually stellar maternity wards, where gravity slowly gathers material together until nuclear fusion ignites, bringing new stars to life. The Eagle Nebula, the Orion Nebula, and countless other star-forming regions are sculpting the future of our galaxy, one newborn star at a time. The galaxy breathes through a process that redistributes material across vast distances. Hot gas rises from the galactic disk into the halo above, cools over millions of years, then rains back down to fuel future generations of stars. This galactic fountain operates on timescales so vast that entire civilizations could rise and fall during a single cycle. Yet this breathing process is essential for maintaining the delicate balance that allows star formation to continue throughout the galaxy's lifetime. Rogue planets drift through our galaxy in numbers that stagger the imagination. Not all worlds orbit stars. Billions of planets have been ejected from their birth systems, condemned to wander the galaxy alone in eternal darkness. These orphan worlds, some possibly retaining internal heat for billions of years, represent a hidden population that may outnumber the planet's orbiting stars. They drift silently through the space between solar systems, invisible reminders of the chaotic early days when planetary systems were still settling into stable configurations. The spiral arms of our galaxy are not permanent features, but waves of density that sweep through the disk. Like traffic jams on a cosmic highway, these density waves compress gas and dust, triggering star formation as they pass. The spiral pattern we see is actually a slow-moving wave that takes hundreds of millions of years to complete one rotation. Stars are born within these waves, shine brilliantly for their lifetimes, then drift out of the spiral arms as the density wave moves on. Hypervelocity stars race through our galaxy at speeds that shouldn't be possible. These cosmic speed demons, moving at over 1,000 kilometers per second, have been flung from the galactic center by gravitational interactions with the supermassive black hole. Some are traveling so fast, they will Milky Way entirely, becoming eventually escape the galactic wanderers. Discovering these stellar refugees has given astronomers new insights into the violent processes occurring near Sagittarius A star. The galactic center is shrouded in mystery and hidden from our direct view. Thick clouds of interstellar dust block visible light from reaching us, but radio waves and infrared radiation can penetrate this cosmic fog. When astronomers peer through these wavelengths, they reveal a region unlike anywhere else in the galaxy. The central few light years contain more mass than millions of typical stars, compressed into a space smaller than our solar system. This central engine drives phenomena that influence the entire galaxy. Ancient globular clusters serve as galactic time capsules, preserving conditions from the universe's youth. These tightly packed spheres of stars, some containing over 1 million individual suns, formed when the Milky Way was still young and turbulent. The stars within globular clusters are metal poor, meaning they formed before generations of stellar deaths had enriched the galaxy with heavy elements. Studying these ancient stellar cities helps astronomers understand how galaxies evolved from the simple conditions of the early universe. The local bubble surrounds our solar system like a protective cocoon. We live inside a region of space that has been cleared of dense material by ancient supernova explosions. This bubble of hot, thin gas extends for hundreds of light years in all directions, creating a relatively empty cavity in what would otherwise be a much denser interstellar medium. The walls of this bubble glow faintly in X-rays, marking the boundary between our local environment and the more typical conditions found elsewhere in the galactic disk. Stellar streams wrap around our galaxy like cosmic ribbons, marking the destruction of smaller galaxies. When a dwarf galaxy ventures too close to the Milky Way, our galaxy's powerful tidal forces stretch it into long, thin streams of stars. These stellar streams can wrap around the galaxy multiple times, creating intricate patterns that astronomers are still mapping. Each stream tells the story of a smaller galaxy that was sacrificed to fuel the growth of our own cosmic home. The thick disk of our galaxy contains stars with a different history than those in the thin disk where we reside. This population of stars has different orbital characteristics and chemical compositions, suggesting they formed during a more chaotic period in the galaxy's past. The thick disk may be the remnant of smaller galaxies that merged with the Milky Way billions of years ago. Their stars now integrated into our galaxy's structure, but retaining the signature of their violent incorporation. Magnetized gas flows throughout the galaxy, carry energy and particles across vast distances. The interstellar medium is not empty space, but a complex network of gas, dust, and magnetic fields that interact in ways we're only beginning to understand. These magnetic fields can channel cosmic rays along specific paths, influence how stars form, and even affect the evolution of entire star-forming regions. The galaxy's magnetic field is weak compared to Earth's, but its enormous scale makes it a powerful force in galactic evolution. The galactic halo extends much farther than the visible galaxy, possibly reaching halfway to Andromeda. This vast spherical region contains most of the galaxy's dark matter, ancient stellar streams, and a sparse population of old stars. The halo is where we find evidence of the Milky Way's cannibalistic past, with stellar debris from consumed galaxies still orbiting long after their parent systems were destroyed. Understanding the structure of the halo is crucial for mapping the galaxy's total mass and gravitational influence. Supernova explosions in our galaxy create cavities in the interstellar medium that persist for millions of years. When massive stars explode, they blast away surrounding material, creating hot bubbles of gas that can span hundreds of light years. These supernova remnants continue expanding for millennia, eventually merging with other bubbles to create even larger structures. The energy from these explosions helps regulate star formation throughout the galaxy by heating and dispersing the raw materials needed to build new stars. The galactic year marks time on a scale that dwarfs human history. Our solar system's orbit around the galactic center takes approximately 225 million Earth years to complete. During the last galactic year, complex life was just beginning to develop on our planet. The next time we return to this position in our orbit, the Sun will be noticeably older, and Earth's continents will have drifted to entirely new positions. Stellar collisions, though rare, do occur in the densest regions of our galaxy. In the crowded cores of globular clusters and near the galactic center, stars can pass close enough to interact gravitationally or even merge directly. These stellar encounters can create exotic objects like blue stragglers, stars that appear younger than their neighbors because they've been rejuvenated by consuming material from a companion. Such collisions remind us that even in the vastness of space, the universe can be a surprisingly crowded place. The chemistry of star formation varies dramatically across different regions of the galaxy. Stars forming in the metal-rich inner regions have access to abundant heavy elements, while those born in the outer reaches or in ancient populations must make do with primarily hydrogen and helium. This chemical gradient affects everything from the types of planets that can form to the likelihood that life might emerge. Our solar system's location in the galaxy may be particularly favorable for the development of rocky planets with the right chemical ingredients for life. The galactic fountain operates like a vast recycling system, moving material between different regions of the Milky Way. Hot gas heated by stellar winds and supernova explosions rises into the galactic halo, where it cools and eventually falls back toward the disk. This process helps distribute heavy elements created by dying stars throughout the galaxy, ensuring that each new generation of stars has access to the chemical building blocks needed to form rocky planets and potentially life itself. Radio observations have revealed that our galaxy is filled with invisible structures that reshape our understanding of its architecture. Vast filaments of neutral hydrogen gas connect different regions of the Milky Way, while bubbles and cavities mark the locations of ancient stellar explosions. These structures, invisible to optical telescopes, create a hidden landscape that influences how matter moves throughout the galaxy and where new stars are most likely to form. The rotation curve of our galaxy reveals the presence of dark matter in ways that continue to puzzle astronomers. Based on the visible matter alone, stars in the outer regions should orbit much more slowly than they actually do. The fact that they maintain high orbital speeds indicates the presence of a massive dark matter halo that extends far beyond the visible galaxy. This discovery was one of the first strong pieces of evidence for dark matter's existence and remains one of the most compelling mysteries in modern astrophysics. As we delve deeper into these galactic mysteries, each revelation opens new questions about the nature of our cosmic home. The Milky Way is not simply a collection of stars scattered through space, but a dynamic, evolving system where every component influences every other part in a cosmic dance that has been unfolding for over 13 billion years. The Milky Way's central bar is a massive stellar highway that most people never realize exists. When astronomers first mapped our galaxy, they expected to find a simple spiral structure. Instead, they discovered that the central region is dominated by an enormous bar of stars stretching across tens of thousands of light years. This galactic bar rotates as a solid structure, funneling gas and dust toward the center where it feeds the supermassive black hole. The bar's gravitational influence shapes the entire inner galaxy, creating the beautiful spiral arms that give our galaxy its classic appearance. Cosmic rays from our galaxy constantly bombard Earth, carrying messages from distant stellar explosions. Every second, billions of high-energy particles streak through the atmosphere and even through your body, most originating from supernova explosions within the Milky Way. These cosmic messengers have traveled for thousands of years across the galaxy before information about the reaching us, carrying violent processes that created them. Some cosmic rays are so energetic that they must have originated from the most extreme environments in our galaxy, possibly near the central black hole itself. The galaxy's magnetic field creates invisible highways for charged particles that span thousands of light years. Like a vast electrical circuit, magnetic field lines thread through the interstellar medium, guiding the motion of cosmic rays and influencing how gas clouds collapse to form new stars. These magnetic highways are constantly shifting and reconnecting, sometimes explosively releasing stored energy in events that can be detected from Earth. The galactic magnetic field is one of the least visible but most important components of our galaxy's infrastructure. Stellar winds from massive stars carve enormous cavities in the space around them. The most massive stars in our galaxy burn so fiercely that they blast material into space at speeds of thousands of kilometers per second. These stellar winds can clear regions hundreds of light years across, creating hot bubbles in the interstellar medium that persist long after the stars themselves have died. When multiple massive stars form in the same region, their combined winds can blow material completely out of the galactic disk. The Milky Way's warp becomes apparent when viewed from the right angle. Our galaxy is not perfectly flat, but twisted like a warped record, with one edge tilted up and the other tilted down. This warping may be caused by gravitational interactions with our satellite galaxies or with dark matter structures in the galactic halo. The warp is most pronounced in the outer regions, where the galactic disk is thinner and more easily influenced by external forces. Tidal streams from disrupted galaxies create a complex web of stellar debris around the Milky Way. As our galaxy consumes smaller neighbors, their stars are stretched into long ribbons that can wrap around us multiple times. The Sagittarius Stream, one of the most prominent examples, extends completely around the sky and represents the ongoing destruction of a dwarf galaxy. These streams are like cosmic archaeology, preserving evidence of mergers that occurred billions of years ago. The local group of galaxies is held together by invisible threads of dark matter. Our galaxy, along with Andromeda and dozens of smaller companions, moves through a vast web of dark matter filaments that connect galaxy clusters across hundreds of millions of light years. These cosmic superhighways channel matter toward gravitational focal points, determining where galaxies form and how they evolve. The local group is just one small neighborhood in this vast cosmic web. Neutron stars in our galaxy are natural laboratories for extreme physics. When the most massive stars collapse, they create objects so dense that a teaspoon of their material would weigh as much as a mountain. These stellar remnants spin at incredible rates, some rotating hundreds of times per second while generating magnetic fields trillions of times stronger than Earth's. Neutron stars push the laws of physics to their limits, creating conditions that cannot be replicated in any earthly laboratory. The galactic plane serves as a natural particle accelerator, stretching across the entire Milky Way. Shock waves from supernova explosions and stellar winds create turbulent regions where particles can be accelerated to incredible energies. These natural accelerators produce cosmic rays that travel throughout the galaxy at nearly the speed of light. Some particles gain so much energy that they rival the most powerful human-made accelerators. Yet they're created by processes that occur naturally throughout the Milky Way. Star formation in our galaxy follows cycles that span hundreds of millions of years. Periods of intense stellar birth alternate with quieter epochs when fewer new stars are born. These cycles may be triggered by the galaxy's passage through spiral density waves, encounters with satellite galaxies, or the accumulation of gas that eventually reaches a critical threshold for collapse. We currently live during a relatively quiet period in this cycle, with star formation proceeding at a steady but modest rate. The thick disk population of stars tells a story of ancient galactic violence. These stars have different orbital characteristics and chemical compositions compared to stars in the thin disk where our solar system resides. They may represent the remnants of smaller galaxies that merged with the Milky Way during its early, more chaotic period. The thick disk serves as a fossil record of our galaxy's turbulent youth, when mergers and interactions were far more common. Interstellar dust grains are cosmic factories producing complex molecules. These tiny particles, smaller than the wavelength of visible light, serve as surfaces where atoms can stick together and form the building blocks of chemistry. In the cold depths of molecular clouds, dust grains become coated with layers of ice containing water, methanol, and other compounds. When new stars form, these enriched dust grains are incorporated into planetary systems, potentially seeding them with the ingredients necessary for life. The galactic center is a region where space and time behave differently than in our neighborhood. The immense gravitational field of the central black hole warps space-time so severely that time passes more slowly there than it does on Earth. Stars orbiting close to the black hole experience extreme tidal forces that stretch them toward their breaking point. Some stars that venture too close are torn apart, their material forming glowing accretion disks that spiral into the black hole. Globular clusters orbit our galaxy like ancient satellites, preserving conditions from the universe's youth. These densely packed stellar cities contain some of the oldest objects in the Milky Way, with ages approaching 13 billion years. The stars in globular clusters formed when the universe contained far fewer heavy elements than it does today. Studying these stellar time capsules helps astronomers understand how the first generation of stars influenced the chemical evolution of galaxies. The local standard of rest defines our galaxy's rotation in a way that reveals hidden motions. This reference frame moves with the average motion of stars in our neighborhood, filtering out the peculiar velocities of individual stars to reveal the underlying rotation of the galactic disk. When astronomers measure stellar motions relative to this standard, they can detect subtle flows and perturbations that hint at the presence of dark matter structures or the gravitational influence of the galactic bar. Stellar streams are being discovered at an accelerating rate as sky surveys become more sensitive. Each newly found stream represents the destruction of a smaller galaxy or star cluster, adding another piece to the puzzle of how the Milky Way assembled itself over cosmic time. Some streams are ancient, with stars that have completed multiple orbits around the galaxy since their parent object was disrupted. Others are relatively fresh, still in the process of being stretched and dispersed by tidal forces. The velocity dispersion of stars increases with their age, creating a natural chronometer for galactic archaeology. Younger stellar populations move in more organized circular orbits around the galactic center, while older stars have had more time to be scattered into eccentric orbits by gravitational interactions. This kinematic heating process allows astronomers to estimate stellar ages based on their orbital properties, providing insights into when different components of the galaxy formed. Massive molecular cloud complexes serve as the galaxy's primary star factories. These giant structures, some containing millions of times the mass of our Sun in gas and dust, are where the majority of new stars are born. The largest complexes can span several hundred light-years and remain active for tens of millions of years before their material is either consumed by star formation or dispersed by stellar winds and supernova explosions. The galactic chemical gradient reveals how elements are distributed throughout the Milky Way. Stars in the inner regions tend to be more metal-rich than those in the outer parts, reflecting the history of stellar nucleosynthesis and the mixing processes that distribute heavy elements throughout the galaxy. This gradient affects the types of planetary systems that can form in different regions, with rocky planets being more common in areas where heavy elements are abundant. Hypervelocity stars provide unique probes of the galactic potential and dark matter distribution. These stellar refugees, ejected from the galactic center at speeds exceeding the escape velocity, trace ballistic trajectories through the galactic halo. By measuring their positions and velocities, astronomers can map the gravitational field of the Milky Way and test models of the dark matter halo that supposedly dominates the galaxy's mass. The Fermi bubbles extend tens of thousands of light-years above and below the galactic plane, marking evidence of past activity from the central black hole. These enormous structures, visible in gamma-ray light, may be the remnants of a period when Sagittarius A star was actively accreting material and launching powerful jets into space. The bubbles are still expanding, carrying energy and material far from the galactic disk into the surrounding halo. Stellar archaeology uses the chemical compositions of ancient stars to reconstruct the early history of galaxy formation. The oldest stars in the Milky Way preserve the chemical signatures of the first supernova that enriched the universe with heavy elements. By analyzing the abundances of different elements in these stellar fossils, astronomers can piece together the sequence of events that led to the formation of our galaxy and the local group. The rotation curve of our galaxy remains flat even at large distances from the center, providing some of the strongest evidence for dark matter. According to the laws of gravity and the distribution of visible matter, stars in the outer regions should orbit much more slowly than those closer to the center. The fact that orbital velocities remain high even in the galaxy's outskirts indicates the presence of a massive invisible halo of dark matter. As we continue exploring these galactic mysteries, each discovery reveals new layers of complexity in our cosmic home. The Milky Way is not a simple collection of stars, but a dynamic, interconnected system where physics plays out on scales both intimate and vast, where the past is written in stellar motions and chemical abundances, and where the future continues to unfold in ways we're only beginning to understand. The interstellar medium of our galaxy is far from the empty void it appears to be. Between the stars lies a complex network of gas, dust, and plasma that spans the entire galactic disk. This material exists in multiple phases, from cold molecular clouds where temperatures hover near absolute zero to hot ionized regions where stellar winds and supernova explosions have heated the gas to millions of degrees. The interstellar medium serves as both the raw material for new star formation and the repository for material ejected by dying stars, creating a continuous cycle of stellar death and rebirth. White dwarf stars in our galaxy represent the ultimate fate of stars like our Sun, but they're far from inactive. These stellar remnants, compressed to incredible densities where a sugar cube-sized piece would weigh as much as a car, continue to influence their surroundings for billions of years. Some white dwarfs exist in binary systems where they slowly steal material from companion stars, occasionally erupting in nova explosions that can briefly outshine entire star-forming regions. These explosions help distribute processed elements throughout the galaxy, contributing to the chemical evolution that makes rocky planets possible. The galaxy's spiral structure is maintained by a delicate balance between stellar orbits and density waves that sweep through the disk like ripples on a pond. Computer simulations reveal that spiral arms are transient features that form, persist for hundreds of millions of years, then dissolve and reform in slightly different configurations. This dynamic behavior means that the Milky Way we see today is subtly different from the galaxy that existed when life first emerged on Earth, and it will continue evolving throughout its future. Pulsar wind nebulae create some of the most energetic environments in our galaxy. When a massive star collapses into a neutron star, it often begins spinning rapidly while generating intense magnetic fields. These pulsars act like cosmic lighthouses, sweeping beams of radiation across space, while simultaneously blowing powerful winds of charged particles into their surroundings. The interaction between these winds and the surrounding interstellar medium creates glowing nebulae that can remain visible for thousands of years after the original supernova explosion. The local arm where our solar system resides is actually a minor spiral feature between two major arms of the galaxy. This location may be particularly favorable for the development of life because it experiences fewer gravitational disruptions from passing stars and less exposure to the intense radiation environments found in the main spiral arms. Our position in this galactic suburb provides a relatively stable environment that has allowed complex chemistry to develop on Earth over billions of years. Stellar nurseries in our galaxy operate like cosmic recycling centers, transforming the debris of dead stars into new stellar generations. When massive stars explode as supernovae, they enrich the surrounding interstellar medium with heavy elements forged in their nuclear cores. These elements become incorporated into new molecular clouds, providing the raw materials for planetary systems that can support rocky worlds and potentially life. Each generation of stars builds upon the chemical legacy of those that came before. The galactic bulge contains some of the oldest stars in the Milky Way, but it's also a region of ongoing stellar formation. This central concentration of stars formed early in the galaxy's history through rapid mergers and gas infall. Today, the bulge continues to evolve as stars migrate inward from the disk and as gas flows along the galactic bar toward the central regions. The complex kinematics of bulge stars provide clues about the violent processes that shaped the galaxy's central regions billions of years ago. Molecular massors scattered throughout our galaxy act as natural amplifiers, creating some of the brightest radio sources in the sky. These cosmic spotlights form when molecules in star-forming regions or around evolved stars become excited by intense radiation, causing them to emit coherent radio waves. Water masers, methanol masers, and other species serve as sensitive probes of the physical conditions in these extreme environments, allowing astronomers to study stellar birth and death processes in unprecedented detail. The galaxy's escape velocity varies dramatically with distance from the center, creating natural boundaries that determine which objects can remain gravitationally bound. In the inner regions, the escape velocity exceeds 1,000 kilometers per second, requiring enormous energies to eject material completely from the galaxy. However, in the outer halo where the gravitational field is weaker, much lower velocities are sufficient for objects to break free and join. Stellar encounters. The intergalactic medium, though rare, have shaped the architecture of planetary systems throughout our galaxy. When stars pass within a few light years of each other, their gravitational fields can disrupt the orbits of planets and smaller bodies, sometimes ejecting them into interstellar space. These encounters may explain the population of rogue planets that drift between the stars, and they provide natural experiments that test our understanding of planetary system dynamics under extreme conditions. The thick disk component of our galaxy may contain clues about the nature of dark matter and its role in galaxy formation. The stars in this component have different orbital characteristics and ages compared to the thin disk population, suggesting they formed during a different epoch in galactic evolution. Some models propose that the thick disk represents stars scattered from the thin disk by gravitational interactions with dark matter substructures, providing a potential observational signature of dark matter's properties. Circumstellar disks around young stars in our galaxy are the birthplaces of planetary systems, and recent observations reveal them to be far more complex and dynamic than previously imagined. These disks contain intricate structures, including gaps, rings, and spiral patterns that may be carved by forming planets. The chemical composition of these disks varies with distance from the central star, creating different zones where rocky planets, gas giants, or icy bodies preferentially form. The galactic fountain process operates on multiple scales, from local bubbles created by individual stellar associations to galaxy-wide flows that redistribute material between the disk and halo. Observations in different wavelengths reveal a complex three-dimensional structure of hot gas rising from the disk, cooling in the halo, and eventually raining back down to fuel future star formation. This circulation pattern helps regulate the rate at which stars form and influences the chemical evolution of different galactic components. Brown dwarfs, often called failed stars, populate our galaxy in numbers that may rival or exceed the population of normal stars. These objects form like stars, but lack sufficient mass to sustain nuclear fusion in their cores. Instead, they slowly cool and fade over billions of years, becoming increasingly difficult to detect. Recent surveys have revealed that brown dwarfs span a wide range of masses and temperatures, with the coolest examples having surface temperatures lower than boiling water. The galactic center contains a dense cluster of young, massive stars that shouldn't exist so close to the supermassive black hole. The intense tidal forces in this region should prevent normal star formation. Yet observations reveal stars less than a few million years old orbiting within light years of Sagittarius A star. These paradoxical objects may have formed elsewhere and migrated inward, or they might represent a completely different mode of star formation that operates under extreme conditions. Stellar streams provide natural laboratories for studying dark matter on galactic scales, As tidal forces stretch these disrupted satellites into long ribbons of stars, the details of their morphology depend sensitively on the gravitational potential they move through. Subtle variations in stream widths, gaps, and orbital properties can reveal the presence of dark matter substructures that are otherwise invisible, making streams powerful tools for testing theories of dark matter and galaxy formation. The local bubble surrounding our solar system is part of a larger network of connected cavities carved by stellar feedback. This superbubble complex, known as the local superbubble, extends for over 1,000 light-years in some directions and connects our local cavity to similar structures throughout the galactic neighborhood. The walls of these bubbles glow in soft X-rays and far ultraviolet light, mapping the three-dimensional structure of hot gas in our region of the galaxy. Hypervelocity stars ejected from the galactic center carry information about the central black hole's properties and past activity. The velocities and trajectories of these stellar refugees depend on the mass and spin of Sagittarius A star, as well as the presence of any intermediate mass black holes that might exist in the galactic nucleus. By studying the population of hypervelocity stars, astronomers can probe conditions in the galactic center that are impossible to observe directly. The chemical abundance patterns in different stellar populations reveal the sequence of nucleosynthetic processes that enriched our galaxy with heavy elements. The oldest stars show the signatures of the first supernova that exploded when the universe was young, while intermediate age populations reflect the contributions of both core collapse and thermonuclear supernovae. The youngest stars, including our Sun, contain elements produced by a wide variety of stellar sources, creating the chemical complexity necessary for rocky planets and life. Magnetic reconnection events in the galactic center create powerful flares that can be detected throughout the electromagnetic spectrum. When magnetic field lines in the accretion flow around Sagittarius A star become tangled and suddenly reconnect, they release enormous amounts of energy in brief, intense bursts. These events provide insights into the fundamental physics of magnetic fields in extreme gravitational environments, and may help explain some of the mysterious high-energy phenomena observed from the galactic nucleus. The rotation curve of our galaxy continues to provide new surprises as more precise measurements become available. Recent data from the Gaia spacecraft have revealed subtle deviations from perfectly circular orbits that hint at the presence of non-axisymmetric structures in the dark matter halo. These discoveries are forcing astronomers to reconsider their models of how dark matter is distributed throughout the galaxy and how it influences stellar motions. Wolf-Rayet stars represent one of the most extreme phases of stellar evolution, burning so intensely that they blast their outer layers into space at thousands of kilometers per second. These stellar blast furnaces are rare, but critically important for the chemical evolution of galaxies. Their powerful winds create enormous cavities in the interstellar medium and enrich their surroundings with carbon, oxygen, and other elements that will eventually be incorporated into new stars and planets. The vertical structure of our galactic disk reveals a complex interplay between stellar heating processes and the gravitational potential. Young stars are confined to a thin layer only a few hundred light-years thick, while older populations have been scattered into a thicker distribution by gravitational encounters and disk heating events. This vertical structure provides a record of the galaxy's dynamical history and helps constrain models of how stellar disks evolve over cosmic time. Circumgalactic medium surrounding our galaxy extends far beyond the visible stellar disk, creating a vast reservoir of hot gas that may contain more mass than all the stars combined. This tenuous atmosphere is constantly being replenished by stellar winds and supernova explosions, while simultaneously being stripped away by interactions with the intergalactic medium. The balance between these processes determines how much gas remains available for future star formation. The galactic magnetic field exhibits complex structures, including reversals, loops, and turbulent regions that challenge our understanding of how magnetic fields are generated and maintained in rotating galaxies. Observations of polarized radio emission from cosmic ray electrons reveal that the field follows the spiral arms in some regions, while showing completely different orientations in others. These patterns provide clues about the dynamo processes that amplify weak seed fields into the structured magnetic patterns we observe today. Stellar black holes scattered throughout our galaxy represent the endpoints of massive stellar evolution, but they're extremely difficult to detect unless they're actively accreting material from a companion star. Recent gravitational wave detections have revealed that stellar mass black holes are more common and more massive than previously expected, suggesting that our galaxy may contain millions of these invisible objects. The merger rate of black hole binaries indicates that gravitational wave astronomy will continue providing new insights into the hidden black hole population. As we venture deeper into these galactic revelations, the picture that emerges is one of breathtaking complexity and beauty. Our Milky Way is not simply a static collection of stars scattered through space, but a living, breathing system where every component influences every other part in an intricate cosmic dance that has been unfolding for over 13 billion years. Each discovery opens new windows into understanding our place in this magnificent spiral of stars, gas, and mystery that we call home. Globular clusters that orbit our galaxy contain stellar populations so ancient they challenge our understanding of cosmic chronology. Some of these densely packed spheres harbor stars that appear to be older than current estimates for the age of the universe itself, creating what astronomers call the age paradox. These stellar time capsules formed when the Milky Way was still assembling from smaller fragments, and their chemical compositions preserve the memory of a universe that contained almost no elements heavier than hydrogen and helium. The most metal-poor stars in these clusters shine with light that began its journey when the cosmos was less than a tenth of its current age. The galactic anticenter region, directly opposite from the galactic nucleus, reveals structures that hint at our galaxy's complex gravitational environment. This direction provides the clearest view through the galactic disk, allowing astronomers to probe the far side of the Milky Way and discover evidence of warping stellar streams and asymmetries that suggest ongoing interactions with satellite galaxies. The anticenter also contains some of the most distant molecular clouds and star-forming regions that are still gravitationally bound to our galaxy. Millisecond pulsars scattered throughout the galaxy serve as natural atomic clocks, their rotation periods stable to within nanoseconds over decades of observation. These rapidly spinning neutron stars have been spun up by accreting material from companion stars, a process that can accelerate their rotation to hundreds of revolutions per second. Arrays of these cosmic chronometers are being used to detect gravitational waves from supermassive black hole mergers occurring in distant galaxies, turning the entire galaxy into a gravitational wave detector. The vertical gradient in stellar metallicity within our galactic disk tells a story of how heavy elements have been mixed and distributed over billions of years. Stars closer to the galactic plane tend to be more enriched in metals than those at greater heights, reflecting the efficiency of mixing processes and the history of stellar feedback. This chemical stratification affects the types of planetary systems that can form at different galactic latitudes, with implications for where habitable worlds might be most common. Stellar associations represent loose groupings of young stars that share common origins, but are gradually dispersing due to their mutual gravitational interactions and the tidal forces of the galaxy. Unlike tightly bound star clusters, these associations are temporary structures that dissolve over tens of millions of years as their member stars drift apart. Many of the brightest stars in our night sky, including several in the constellation Orion, belong to associations that are slowly expanding and fading into the general stellar population. The galactic thin disk exhibits a complex age-metallicity relation that chronicles the chemical enrichment history of star-forming gas over cosmic time. Older stellar populations tend to be more metal-poor than younger ones, but the relationship is not perfectly monotonic, revealing episodes of enhanced star formation, gas infall events, and mixing processes that have complicated the galaxy's chemical evolution. These patterns help from dying astronomers understand how feedback stars has of subsequent stellar influenced the composition generations. Co-rotation resonances within our galaxy create stable regions where stars and gas can maintain synchronized orbits with the spiral pattern. These gravitational sweet spots allow material to accumulate and persist within the spiral arms for extended periods, enhancing star formation efficiency and creating the prominent dust lanes visible in other spiral galaxies. Our solar system's current position relative to these resonances may help explain the relatively stable conditions Earth has experienced over geological time scales. The local standard of rest reveals subtle streaming motions in our stellar neighborhood that reflect the influence of non-axis symmetric structures within the galactic potential. Groups of stars moving with similar velocities create kinematic substructure that may trace dissolved star clusters, the gravitational wake of spiral density waves, or perturbations caused by dark matter subhalos. These velocity patterns provide forensic evidence for dynamical processes that have shaped our local galactic environment. Circumstellar shells around evolved stars contribute significantly to the enrichment of the interstellar medium with processed elements. As intermediate mass stars progress through their red giant phases, they shed substantial fractions of their mass through stellar winds, creating expanding bubbles of gas enriched with carbon, nitrogen, and other products of nuclear burning. These shells eventually merge with the broader interstellar medium, providing raw materials for future generations of stars and planets. The galactic fountain model explains how energy and material are exchanged between the disk and halo through a continuous cycle of heating, rising, cooling, and falling gas. Supernova explosions and stellar winds inject energy into the interstellar medium, driving hot gas upward into the galactic halo where it can cool and condense before raining back down onto the disk. This circulation pattern helps regulate star formation rates and distributes heavy elements throughout the galaxy's three-dimensional structure. Stellar radial migration allows stars to change their galactic orbits over time, mixing populations that formed at different distances from the galactic center. Gravitational interactions with spiral arms, stellar bars, and other non-axisymmetric features can cause stars to migrate either inward or outward from their birth locations. Our Sun may have formed closer to the galactic center and gradually migrated to its current position, carrying with it the chemical signature of its original birthplace. The galactic bulge exhibits a complex box peanut shape when viewed edge-on, reflecting the three-dimensional structure created by the central stellar bar. This morphology results from the vertical buckling instability that affects barred galaxies, causing stars to move in complex orbits that create the characteristic peanut-shaped profile. The kinematics of bulge stars provide insights into the formation mechanism of galactic bars and their role in driving gas toward central black holes. Molecular cloud turbulence plays a crucial role in regulating the star formation process throughout our galaxy. The supersonic motions observed within these clouds create a complex hierarchy of structures from the largest cloud complexes down to individual stellar cores. This turbulent cascade helps support clouds against gravitational collapse, while simultaneously creating the density fluctuations necessary for star formation. Understanding this turbulence is key to predicting where and when new stars will form. The galactic warp extends well beyond the stellar disk into the outer regions dominated by neutral hydrogen gas. Radio observations reveal that this warping becomes more pronounced at larger galactic radii, where the gravitational restoring force of the central mass concentration becomes weaker. The warp may be a response to torques exerted by the large and small Magellanic Clouds, or to the accretion of material with angular momentum misaligned with the galactic disk. Stellar multiplicity statistics reveal that most stars in our galaxy are born as members of binary or multiple star systems. Only about half of all stars remain single throughout their lifetimes, while the others experience complex evolutionary processes influenced by their companions. These interactions can lead to mass transfer, common envelope phases, and even stellar mergers that create exotic objects not predicted by single-star evolution models. The interstellar radiation field pervades our galaxy, providing the energy source that ionizes gas, heats dust grains, and drives photochemical reactions processes in molecular clouds. This background radiation consists of contributions from all the stars in the galaxy, creating a complex three-dimensional field that varies with position and influences the physical conditions throughout the interstellar medium. The radiation field plays a particularly important role in regulating the balance between atomic and molecular hydrogen in different galactic environments. Galactic chemical evolution models attempt to reproduce the observed abundance patterns by tracking the production and distribution of elements over cosmic time. These models must account for the contributions from different types of supernovae, stellar winds from massive stars, and nucleosynthesis in intermediate mass stars, while also considering how gas flows, star formation efficiency, and mixing processes affect the chemical evolution. The most successful models suggest that our galaxy has experienced a complex history of gas accretion and stellar feedback. The Perseus arm and Sagittarius arm represent the two major spiral features that bracket our location in the local arm. These structures are traced by young massive stars, emission nebulae, and molecular cloud complexes that outline the galaxy's spiral pattern. The gravitational influence of these density waves affects stellar orbits throughout the disk and may be responsible for triggering episodes of enhanced star formation as gas clouds are compressed during their passage through the spiral arms. High-velocity clouds surrounding our galaxy may represent either primordial gas that has never been processed through stars or material expelled from the galactic disk by fountain flows and stellar feedback. These diffuse structures contain substantial amounts of neutral hydrogen and are gradually being accreted onto the galaxy, potentially providing fuel for continued star formation. Some high-velocity clouds show evidence of ongoing star formation, suggesting they may be the building blocks from which dwarf galaxies form. The galactic center GeV excess detected in gamma-ray observations has sparked intense debate about its origin and implications for dark matter physics. This spherically symmetric emission extending several degrees from the galactic nucleus exhibits spectral characteristics consistent with dark matter annihilation, but it could also arise from a previously unrecognized population of millisecond pulsars or other astrophysical sources. Resolving this mystery may provide crucial insights into the nature of dark matter, or reveal new classes of high-energy phenomena in galactic centers. Stellar archaeology techniques use the detailed chemical abundances of individual stars to reconstruct the assembly history of our galaxy. Each star preserves the chemical signature of the gas from which it formed, creating a fossil record of nucleosynthetic processes and mixing events that occurred throughout galactic history. By analyzing large samples of stars with different ages and kinematics, astronomers can trace the contributions from different stellar sources and map how the galaxy's chemical composition has evolved over time. The local group's motion through the cosmic web reflects the gravitational influence of much larger structures, including the Virgo cluster and the Great Attractor. Our entire galactic neighborhood is falling toward these massive concentrations of matter at hundreds of kilometers per second, participating in flows that span hundreds of millions of light years. These bulk motions provide information about the large-scale distribution of matter and the growth of cosmic structure over billions of years. Superbubbles created by stellar associations can grow to enormous sizes, sometimes breaking through the galactic disk and venting hot gas into the halo. When multiple massive stars in a region explode as supernovae within a few million years of each other, their combined energy can excavate cavities spanning hundreds of light years. These structures create chimneys that allow material processed in stellar cores to escape the disk and enrich the circumgalactic medium with heavy elements. The galactic habitable zone concept suggests that there may be optimal regions within our galaxy for the development of complex life. This zone would avoid the radiation-rich inner regions near the galactic center, while also avoiding the metal-poor outer regions where rocky planets may be rare. The boundaries of this habitable zone depend on many factors, including the local star formation rate, supernova frequency, and the availability of heavy elements necessary for planet formation. Magneto-rotational instability in accretion flows around stellar remnants, and the central black hole provides a mechanism for transporting angular momentum and driving material inward. This process is fundamental to understanding how compact objects can accrete matter efficiently and power the high-energy phenomena observed throughout our galaxy. The same instability may also operate in protoplanetary disks, influencing the formation and migration of planets around young stars. The age gradient observed in the galactic disk reflects the inside-out formation scenario in which the inner regions assembled earlier and more rapidly than the outer parts. Stars in the inner galaxy tend to be older and more metal-rich than those at larger radii, consistent with models in which star formation began in the central regions and gradually extended outward as gas was accreted and angular momentum was redistributed within the forming galaxy. Stellar feedback processes, including radiation pressure, stellar winds, and supernova explosions, play crucial roles in regulating star formation efficiency throughout our galaxy. These mechanisms can disrupt star-forming molecular clouds, drive turbulence in the interstellar medium, and launch galactic-scale outflows that remove gas from star-forming regions. The balance between gravitational collapse and stellar feedback determines how efficiently gas is converted into stars and influences the overall evolution of galactic structure. The discovery of hypervelocity stars has opened new avenues for probing the gravitational potential of our galaxy and testing theories of stellar dynamics in extreme environments. These objects, traveling at speeds exceeding the local escape velocity, provide unique tracers of the dark matter halo and can reveal the presence of intermediate mass black holes or other exotic objects that might exist in the galactic center. The trajectories of hypervelocity stars also constrain the mass and shape of the Milky Way's gravitational field. Dust extinction creates a complex, three-dimensional map of obscuring material throughout our galaxy, with implications for understanding star formation, stellar populations, and galactic structure. The patchy distribution of interstellar dust creates variations in the apparent brightness and color of stars that depend on their distance and the properties of intervening material. Modern surveys are creating detailed three-dimensional maps of dust distribution that reveal the locations of molecular clouds, supernova remnants, and other structures in the interstellar medium. The thick disk population exhibits kinematic and chemical properties that distinguish it from both the thin disk and stellar halo populations. These stars may represent material scattered from the early thin disk by minor mergers, stars accreted from disrupted satellites, or a distinct component that formed during a different epoch in galactic evolution. Understanding the origin of the thick disk provides important constraints on models of galaxy formation and the role of mergers in shaping galactic structure. As we continue peeling back the layers of mystery surrounding our galactic home, each revelation adds another piece to the vast puzzle of how the Milky Way formed, evolved, and continues to change. The galaxy emerges not as a simple stellar island floating in space, but as a complex ecosystem where gravity, magnetism, stellar evolution, and dark matter interact across scales spanning from individual stars to the cosmic web itself. These ongoing discoveries remind us that our understanding of even our own cosmic neighborhood remains incomplete, with new surprises waiting to be uncovered by future observations and theoretical insights. Galactic cannibalism occurs on timescales that dwarf human comprehension, as our Milky Way slowly devours its smaller neighbors in a process that has been ongoing for billions of years. The remnants of these ancient meals can still be detected today as streams of stars that wrap around our galaxy like ghostly ribbons, each one marking the death of a smaller stellar system. The Sagittarius dwarf galaxy is currently being torn apart by our galaxy's immense gravitational field, stretched into a long trail of stars that extends completely around the sky. This ongoing destruction provides a real-time example of how large galaxies grow by consuming their neighbors. The Milky Way's stellar population exhibits a complex age structure that reflects its turbulent formation history. The oldest stars, found primarily in the galactic halo and thick disk, formed when the universe contained almost no heavy elements beyond hydrogen and helium. These ancient suns shine with a distinctly different color than younger stars, their spectra revealing the chemical signatures of a much simpler cosmos. As successive generations of stars lived and died, they enriched the galaxy with increasingly complex chemistry, eventually creating the conditions necessary for rocky planets and the emergence of life. Stellar winds from evolved stars create some of the most beautiful and scientifically important structures in our galaxy. When intermediate mass stars enter their final phases of evolution, they shed their outer layers in spectacular displays that can be seen across thousands of light years. These planetary nebulae, despite their misleading name, have nothing to do with planets, but instead represent the glowing shrouds of gas expelled by dying stars. The intricate shapes and colors of these nebulae result from complex interactions between stellar winds, magnetic fields, and the surrounding interstellar medium. The galactic magnetic field exhibits a complex structure that influences virtually every aspect of the Milky Way's behavior. This invisible force field threads through the entire galaxy, channeling the flow of cosmic rays, shaping the collapse of molecular clouds, and affecting the formation of new stars. The field strength varies dramatically across different regions, reaching its maximum intensity near the galactic center, where it becomes strong enough to influence the motion of charged particles at relativistic speeds. Understanding these magnetic phenomena is crucial for comprehending how energy and matter move throughout our galaxy. Molecular masers scattered throughout the Milky Way act as natural radio beacons, amplifying specific frequencies of radiation to create some of the brightest sources in the radio sky. These cosmic spotlights form when molecules in star-forming regions or around evolved stars become pumped to excited states by intense radiation fields. Water masers, methanol masers, and other molecular species serve as sensitive probes of the physical conditions in regions where new stars are being born or where old stars are dying, providing insights into processes that would otherwise be hidden from direct observation. The local standard of rest provides a reference frame that filters out the random motions of individual stars to reveal the underlying rotation pattern of our galactic neighborhood. When astronomers measure stellar velocities relative to this standard, they can detect subtle deviations that hint at the presence of gravitational perturbations caused by spiral density waves, stellar bars, or dark matter substructures. These kinematic signatures provide forensic evidence for dynamical processes that have shaped our local environment over millions of years. Brown dwarfs represent a hidden population of substellar objects that may be nearly as numerous as ordinary stars in our galaxy. These failed stars form through the same gravitational collapse process as normal stars, but lack sufficient mass to sustain hydrogen fusion in their cores. Instead, they slowly cool and fade over billions of years, becoming increasingly difficult to detect as they age. Recent infrared surveys have revealed that brown dwarfs exhibit a surprising diversity of properties, with the coolest examples having surface temperatures lower than boiling water and atmospheres containing exotic clouds made of liquid iron droplets. The galactic fountain operates as a vast circulation system that redistributes material between the disk and halo over timescales of hundreds of millions of years. Hot gas heated by supernova explosions and stellar winds rises into the galactic halo, where it cools and eventually rains back down onto the disk to fuel future generations of star formation. This process helps regulate the chemical evolution of the galaxy by mixing heavy elements produced in stellar cores throughout the three-dimensional structure of the Milky Way. Circumstellar disks around young stars serve as the birthplaces of planetary systems, exhibiting complex structures that reveal the planet formation process in action. These disks contain intricate patterns, including gaps, rings, and spiral features that are carved by the gravitational influence of forming planets. The chemical composition of disk material varies with distance from the central star, creating different zones where rocky planets, gas giants, or icy bodies preferentially form. Recent observations have revealed that these disks are far more dynamic and structured than previously imagined. The thick disk component of our galaxy preserves evidence of ancient merger events that occurred during the Milky Way's early assembly phase. Stars in this population exhibit different orbital characteristics and chemical abundances compared to the thin disk where our solar system resides, suggesting they originated in smaller galaxies that were subsequently incorporated into our own. The kinematics of thick disk stars provide constraints on the mass and timing of these ancient collisions, helping astronomers reconstruct the violent early history of galactic formation. Hypervelocity stars ejected from the galactic center carry information about the extreme gravitational environment surrounding our central black hole. These stellar refugees, traveling at speeds exceeding 1,000 kilometers per second, were likely accelerated by close encounters with Sagittarius A star or by the disruption of binary star systems in the dense nuclear region. Some of these stars are moving so rapidly that they will eventually escape the galaxy entirely, becoming intergalactic wanderers that preserve the chemical signatures of our galactic center in their stellar atmospheres. The interstellar radiation field creates a complex three-dimensional environment that influences the physical and chemical conditions throughout our galaxy. This background of starlight provides the energy needed to ionize gas, heat dust grains, and drive photochemical reactions in molecular clouds. The intensity and spectral characteristics of this radiation field vary dramatically with position in the galaxy, creating different environments for star formation and affecting the types of molecules that can survive in different regions. Stellar associations represent loose groupings of young stars that share common origins, but are gradually dispersing under the influence of galactic tidal forces. Unlike gravitationally bound star clusters, these associations are temporary structures that dissolve over tens of millions of years as their member stars drift apart on independent orbits. Many of the most prominent stars in our night sky belong to associations that are slowly expanding and fading into the general stellar population, creating moving groups that can be traced through their common space velocities. The galactic chemical gradient reflects billions of years of stellar nucleosynthesis and the mixing processes that distribute heavy elements throughout the Milky Way. Stars in the inner regions tend to be more metal-rich than those in the outer parts, a pattern that influences the types of planetary systems that can form at different galactic radii. This radial variation in chemical composition affects everything from the formation of rocky planets to the likelihood that complex chemistry might emerge in different parts of the galaxy. Magnetohydrodynamic processes in the interstellar medium create turbulent conditions that influence star formation efficiency throughout our galaxy. The complex interplay between magnetic fields, gas dynamics, and gravitational forces generates a cascade of motions spanning many orders of magnitude in scale. This turbulence helps support molecular clouds against gravitational collapse, while simultaneously creating the density fluctuations necessary for individual stars to form within larger cloud complexes. The local bubble represents a cavity in the interstellar medium that surrounds our solar system, created by ancient supernova explosions that cleared the local environment of dense material. This hot, rarefied region extends for hundreds of light years in all directions, providing a relatively clear window through which we can observe more distant parts of the galaxy. The boundaries of this bubble are marked by shells of compressed gas and dust that glow faintly in various wavelengths of light. Pulsar wind nebulae showcase some of the most extreme physics operating in our galaxy, where rapidly rotating neutron stars accelerate particles to relativistic energies and inject them into the surrounding medium. These cosmic particle accelerators create glowing nebulae that remain visible for thousands of years after the original supernova explosion, serving as laboratories for studying high-energy astrophysics under conditions that cannot be replicated in terrestrial experiments. The age-metallicity relation in our galactic disk chronicles the chemical enrichment history of star-forming gas over cosmic time, revealing episodes of enhanced stellar nucleosynthesis, gas infall events, and mixing processes that have complicated the galaxy's chemical evolution. This relationship between stellar age and heavy element abundance provides insights into how different types of stars have contributed to the chemical complexity we observe today. Co-rotation resonances within the galactic disk create stable orbital configurations where stars and gas can maintain synchronized motion with the spiral density wave pattern. These gravitational sweet spots allow material to accumulate within spiral arms for extended periods, enhancing star formation efficiency and creating the prominent dust lanes visible in images of other spiral galaxies. Our solar system's position relative to these resonances may help explain the relatively stable conditions Earth has experienced. The circumgalactic medium surrounding our galaxy contains a vast reservoir of hot, diffuse gas that may hold more mass than all the stars in the galactic disk combined. This extended atmosphere is constantly being replenished by stellar winds and supernova explosions, while simultaneously being stripped away by interactions with the intergalactic medium. The balance between these processes determines how much fuel remains available for future star formation and influences the long-term evolution of galactic structure. Stellar radial migration allows stars to change their orbits over time, mixing populations that formed at different distances from the galactic center and complicating efforts to reconstruct the galaxy's chemical evolution history. Gravitational interactions with spiral arms, bars, and other can cause stars to migrate axisymmetric features either inward or outward from their birth locations, carrying with them the chemical signatures of their original environments. The galactic bulge exhibits complex three-dimensional structure and kinematics that reflect the violent processes involved in its formation during the early assembly of our galaxy. This central concentration of old stars shows evidence of rapid formation through mergers and gas infall, with subsequent evolution driven by the growth of the central bar and ongoing dynamical interactions. The motions of bulge stars provide crucial constraints on models of how galactic centers form and evolve. High-velocity clouds surrounding the Milky Way may represent either pristine gas that has never been processed through stars or material expelled from the galactic disk by energetic feedback processes. These diffuse structures contain substantial amounts of neutral hydrogen and are gradually being accreted onto the galaxy, potentially providing fuel for continued star formation over the next several billion years. The discovery of gravitational waves from merging stellar mass black holes has revealed that our galaxy likely contains millions of these invisible remnants, far more than previously estimated based on observations of X-ray binaries alone. The merger rate inferred from gravitational wave detections suggests that stellar evolution models may need to be revised to account for the formation of more massive black holes than traditional theories predicted. Superbubbles excavated by multiple supernova explosions can grow large enough to break through the galactic disk and vent hot gas into the surrounding halo. These chimneys allow material processed in stellar cores to escape the dense disk environment and enrich the circumgalactic medium with heavy elements, contributing to the chemical evolution of the galaxy's extended atmosphere. The galactic warp becomes increasingly pronounced at larger radii, where the gravitational restoring force of the central mass distribution becomes weaker. This three-dimensional distortion of the galactic disk may result from torques exerted by satellite galaxies or from the accretion of material with angular momentum misaligned with the main disk plane. Stellar multiplicity statistics indicate that most stars in our galaxy are born as members of binary or higher-order multiple systems, with complex evolutionary consequences that can lead to mass transfer, common envelope phases, and exotic merger products not predicted by single-star evolution models. These interactions play crucial roles in producing many of the most interesting objects in our galaxy, from type Ia supernovae to gravitational wave sources. The Perseus and Sagittarius arms represent the two major spiral features that bracket our location in the local arm, creating the large-scale structure that channels gas flows and influences star formation patterns throughout the galactic disk. The gravitational influence of these density waves affects stellar orbits and may trigger episodes of enhanced stellar birth as molecular clouds are compressed during their passage through the spiral pattern. As we approach the culmination of our journey through these 100 remarkable facts, the Milky Way reveals itself to be far more than a simple collection of stars scattered through space. It emerges as a dynamic, interconnected system where every component, from the smallest dust grain to the most massive black hole, plays a role in an ongoing story of cosmic evolution that stretches back over 13 billion years and continues unfolding today. Molecular cloud complexes scattered throughout our galaxy serve as cosmic nurseries, where the raw materials of stellar death are transformed into the building blocks of new life. These vast structures, some spanning hundreds of light years and containing millions of times the mass of our Sun, represent the galaxy's most productive star formation factories. Within their cold, dark depths, temperatures hover just a few degrees above absolute zero, while densities remain incredibly low by terrestrial standards. Yet these seemingly empty regions are where gravity performs its most delicate work, slowly gathering wisps of gas and dust into ever denser concentrations until the moment arrives when nuclear fusion ignites and a new star blazes to life. Infrared observations have revealed that these star-forming regions exhibit intricate structures invisible to optical telescopes, with complex networks of filaments, cores, and cavities carved by stellar winds and radiation pressure from newly formed massive stars. The interplay between gravity, which seeks to collapse material into ever denser concentrations, and the various forces that resist this collapse, creates a delicate balance that determines how efficiently gas is converted into stars and how many stars form within each cloud complex. The most massive stars born within these nurseries live fast and die young, their brief but spectacular lives ending in violent explosions that can disrupt the very clouds that gave them birth. These stellar titans burn through their nuclear fuel at prodigious rates, shining with the luminosity of millions of suns, while simultaneously blasting powerful winds into their surroundings. When they finally exhaust their fuel and collapse into black holes or neutron stars, the resulting supernova explosions can trigger new waves of star formation in neighboring regions, while simultaneously destroying the molecular clouds in their immediate vicinity. Binary and multiple star systems form commonly within these stellar nurseries, with gravitational interactions during the early stages of stellar evolution determining which stars remain bound to companions and which are ejected as single objects. The complex dynamics of young stellar clusters can lead to close encounters that alter orbital parameters, strip away circumstellar disks, or even result in direct collisions between protostars. These interactions play crucial roles in determining the final masses and properties of the stars that emerge from each star-forming episode. The magnetic fields threading through molecular clouds influence the collapse process in subtle but important ways, providing additional support against gravity while also channeling material flows and affecting the angular momentum distribution within forming stellar systems. These invisible force fields can slow the collapse of dense cores, regulate the accretion rate onto forming protostars, and influence the formation of circumstellar disks where planets will eventually coalesce. Understanding the role of magnetic fields in star formation remains one of the most challenging aspects of stellar birth research. Protoplanetary disks surrounding young stars reveal the planet formation process in exquisite detail, with gaps, rings, and spiral structures marking the locations where forming planets are sweeping up material and gravitationally sculpting their immediate environments. These disks contain the raw materials from which entire planetary systems will emerge, with different regions favoring the formation of rocky terrestrial worlds, gas giant planets, or icy bodies depending on the local temperature and chemical composition. The chemical composition of these disks varies dramatically with distance from the central star, creating distinct zones where different types of planets preferentially form. Close to the star, high temperatures favor the condensation of refractory materials that will become the building blocks of rocky worlds like Earth. Further out, beyond the snow line where water can freeze, icy grains provide the solid foundation upon which gas giant planets can rapidly accumulate massive atmospheres. Recent observations have revealed that planet formation is a remarkably rapid process, with evidence suggesting that giant planets can form within the first few million years of a star's life. This timeline places important constraints on theories of planetary formation and suggests that the basic architecture of planetary systems becomes established very early in stellar evolution, long before the central star reaches the main sequence and begins its stable hydrogen burning phase. The diversity of planetary systems discovered around other stars has revolutionized our understanding of planet formation processes, revealing that our solar system may be somewhat unusual in its configuration, rather than typical of planetary systems in general. Hot Jupiter planets orbiting extremely close to their stars, super-Earth worlds with no analog in our solar system, and planets in highly eccentric or misaligned orbits all challenge traditional models of planetary formation and migration. Stellar feedback processes play crucial roles in regulating star formation efficiency throughout our galaxy. With radiation pressure, stellar winds, and supernova explosions all contributing to the disruption of star-forming molecular clouds. The most massive stars produce such intense radiation fields that they can ionize the gas in their immediate vicinity, creating expanded bubbles of hot plasma that eventually break out of their parent clouds and inject energy into the broader interstellar medium. The cumulative effect of stellar feedback over cosmic time has been to reduce the overall efficiency of star formation, ensuring that only a small fraction of the available gas is converted into stars during each star-forming episode. This regulatory mechanism helps explain why galaxies like the Milky Way have continued forming stars over billions of years rather than consuming all their gas in a single burst of activity during their early evolution. Wolf-Rayet stars represent one of the most extreme phases of massive stellar evolution, with surface temperatures exceeding 50,000 degrees and stellar winds so powerful they can strip away the star's entire hydrogen envelope. These evolutionary descendants of the most massive main sequence stars burn so intensely that they blast material into space at speeds of thousands of kilometers per second, creating expanding shells of processed material that enrich the surrounding interstellar medium with carbon, nitrogen, and other elements forged in stellar cores. The powerful winds from Wolf-Rayet stars carve enormous cavities in the interstellar medium, creating hot bubbles that can persist for millions of years after the stars themselves have exploded as supernovae. These stellar blast furnaces are relatively rare, but critically important for the chemical evolution of galaxies, producing and distributing elements that will eventually be incorporated into new generations of stars and planetary systems. The transition from main sequence star to Wolf-Rayet phase involves the loss of most of the star's original mass, with only the hot, dense core remaining visible as the star approaches the end of its evolutionary journey. This mass loss process is so efficient that stars, which began their lives with masses exceeding 20 times that of the Sun, may retain only a few solar masses by the time they reach the Wolf-Rayet phase. Red supergiant stars represent another pathway for massive stellar evolution, with these bloated giants expanding to enormous sizes as they burn increasingly heavy elements in their cores. Some red supergiants grow so large that they could engulf the orbit of Mars if placed at the center of our solar system. Yet their surfaces remain relatively cool compared to main sequence stars of similar mass. The convective processes operating within red supergiant interiors create complex patterns of material mixing that bring processed elements from the core to the surface, where they can be detected spectroscopically and eventually expelled through stellar winds. These stars serve as important laboratories for studying the advanced stages of nuclear burning that occur in massive stellar cores as they progress through the synthesis of increasingly heavy elements. Variable stars throughout our galaxy pulsate with rhythms that reflect the internal physics of stellar structure and evolution, with some classes exhibiting such regular periodicity that they serve as standard candles for distance measurements throughout the universe. Cepheid variables, RR Lyrae stars, and other pulsating objects follow well-defined relationships between their pulsation periods and intrinsic luminosities, allowing astronomers to determine distances to galaxies millions of light-years away. The pulsation mechanisms driving these stellar lighthouses involve complex interactions between radiation pressure, gravitational forces, and the opacity properties of stellar atmospheres. As the star expands and contracts, changes in temperature and density create periodic variations in brightness that can be detected and measured with remarkable precision using modern photometric techniques. Long-period variables and semi-regular pulsators among the red giant and asymptotic giant branch populations exhibit more chaotic variability patterns that reflect the complex convective processes occurring in their extended atmospheres. These stars are gradually shedding their outer layers through pulsation-driven mass loss, creating the raw materials that will eventually be recycled into future generations of stars and planets. Symbiotic stars represent exotic binary systems, where a cool giant star transfers material to a hot white dwarf companion, creating complex interactions that can lead to nova-like outbursts and the production of highly ionized nebular emission. These systems provide natural laboratories for studying mass transfer processes, thermonuclear burning on white dwarf surfaces, and the evolution of close binary stars. The accretion disks that form around white dwarf stars in these systems can reach temperatures of tens of thousands of degrees, hot enough to produce strong ultraviolet radiation that ionizes the wind material from the giant companion. The resulting nebular emission creates spectacular displays that can be observed across thousands of light years, revealing the intricate details of binary stellar evolution in action. Cataclysmic variables encompass a diverse class of binary systems, where mass transfer from a normal star onto a white dwarf companion leads to dramatic outbursts and complex evolutionary sequences. Classical novae occur when accumulated hydrogen on the white dwarf surface reaches sufficient density and temperature to ignite explosive thermonuclear burning, temporarily increasing the system's brightness by factors of thousands or even millions. Recurrent novae represent systems where the mass transfer rate and white dwarf mass are finely tuned to produce repeated explosive episodes separated by decades or centuries. These systems may be important progenitors of type Ia supernovae, which occur when the white dwarf finally accumulates enough mass to trigger carbon ignition and complete thermonuclear disruption. Dwarf novae exhibit smaller-scale outbursts caused by instabilities in the accretion disk rather than nuclear burning on the white dwarf surface. These systems undergo quasi-periodic brightening episodes as material accumulated in the outer disk suddenly cascades inward, temporarily increasing the accretion rate and heating the disk to higher temperatures. The study of cataclysmic variables has provided crucial insights into accretion physics, binary evolution, and explosive nucleosynthesis processes that operate throughout the universe. These systems serve as nearby laboratories where astronomers can study phenomena that occur around much more distant and powerful objects, such as supermassive black holes in active galactic nuclei. X-ray binaries showcase even more extreme examples of accretion physics, where material falling onto neutron stars or stellar mass black holes releases gravitational potential energy at such high rates that the systems become luminous across the entire electromagnetic spectrum. Low-mass X-ray binaries consist of neutron star or black hole primaries accreting material from evolved companion stars, while high-mass systems involve massive stars transferring material through stellar winds or Roche lobe overflow. The accretion disks in these systems reach temperatures of millions of degrees, hot enough to produce copious X-ray emission that can be detected from thousands of light-years away. The extreme gravitational fields near neutron stars and black holes create relativistic effects that provide unique opportunities to test general relativity and study matter under conditions that cannot be replicated in terrestrial laboratories. Millisecond pulsars represent the end products of the accretion process in low-mass X-ray binaries, where the neutron star has been spun up to rotation periods of just a few milliseconds through the transfer of angular momentum from the accreted material. These rapidly spinning neutron stars serve as incredibly stable cosmic clocks, with rotation periods that can be measured to precisions rivaling the best atomic clocks on Earth. The formation of millisecond pulsars requires a delicate balance between the accretion rate and magnetic field strength of the neutron star, with too high an accretion rate leading to unstable nuclear burning on the surface, and too low a rate failing to provide sufficient angular momentum to spin up the star. The resulting population of millisecond pulsars provides important constraints on binary evolution models and neutron star physics. Pulsar timing arrays using networks of these cosmic chronometers are now detecting gravitational waves from supermassive black hole mergers occurring in distant galaxies, opening an entirely new window on the universe's most violent phenomena. The technique relies on measuring tiny changes in pulsar arrival times caused by gravitational waves stretching and compressing space as they pass between the pulsars and Earth. As our exploration of these galactic wonders continues to unfold, each discovery reveals new layers of complexity and beauty within our cosmic home. The Milky Way emerges not as a static collection of distant lights, but as a dynamic, living system where the fundamental forces of physics play out across scales from subatomic particles to the vast, dark matter halo that encompasses our entire galactic neighborhood. The stellar graveyard of our galaxy contains objects so bizarre they challenge our understanding of physics itself. White dwarf stars represent the most common endpoint for stellar evolution, yet these Earth-sized remnants retain masses comparable to our Sun, creating gravitational fields so intense that a sugar cube of white dwarf material would weigh as much as an automobile. These stellar corpses cool slowly over billions of years, gradually fading from white-hot brilliance to dim red embers that will eventually become invisible black dwarfs in the far future. Some white dwarfs exist in isolation, quietly radiating away their stored thermal energy in the darkness between stars. Others find themselves locked in gravitational embraces with companion stars, stealing material in a cosmic dance that can lead to spectacular explosions. When hydrogen accumulates on a white dwarf surface and reaches critical temperature and pressure, thermonuclear fusion ignites in a runaway process that briefly transforms the system into a classical nova, temporarily outshining entire star clusters. The most massive white dwarfs teeter on the edge of catastrophic collapse, approaching the Chandrasekhar limit, where electron degeneracy pressure can no longer support the star against its own gravity. When this critical threshold is exceeded, either through mass accretion or collision with another white dwarf, the result is a Type Ia supernova that completely destroys the star in a thermonuclear explosion visible across billions of light years. Neutron stars push the boundaries of physics even further, compressing the mass of the Sun into a sphere barely 20 kilometers across. These ultra-dense objects represent matter in its most exotic state outside of black holes, with surface gravity so intense that falling from a height of 1 millimeter would accelerate an object to speeds of hundreds of meters per second by the time it hits the surface. The magnetic fields surrounding neutron stars dwarf anything found elsewhere in the universe, reaching strengths trillions of times more powerful than Earth's protective charged particles to nearly the speed of light, creating beams of radiation that sweep magnetic shield. These invisible force fields can accelerate across space like cosmic lighthouses. When these beams intersect our line of sight, we detect them as pulsars, celestial metronomes that tick with precision rivaling atomic clocks. Some neutron stars spin so rapidly they complete hundreds of rotations per second, their equators moving at significant fractions of light speed, while somehow holding together despite centrifugal forces that would tear apart any normal material. These millisecond pulsars challenge our understanding of how matter behaves under extreme conditions, existing in a regime where general relativity and quantum mechanics intersect in ways we're only beginning to comprehend. Magnetar represents the most extreme class of neutron stars, possessing magnetic fields so powerful they could erase the magnetic stripe on a credit card from thousands of miles away. These stellar remnants occasionally release bursts of energy equivalent to what our sun produces in centuries, flooding nearby space with high-energy radiation that can affect Earth's atmosphere even from distances of tens of thousands of light years. Black holes lurking throughout our galaxy represent the ultimate triumph of gravity over all other forces, creating regions where space-time curvature becomes so extreme that not even light can escape. Stellar mass black holes form when the most massive stars collapse beyond the neutron star threshold, compressing matter to infinite density according to our current understanding of physics. Though quantum effects likely prevent such mathematical singularities from actually forming, the event horizons surrounding these gravitational monsters mark boundaries in space-time beyond which no information can ever return to the outside universe. From an external perspective, matter falling toward a black hole appears to slow down and fade away as it approaches this point of no return, frozen forever at the threshold, while its light becomes increasingly red-shifted until it disappears entirely from view. Hawking radiation represents a quantum mechanical process that allows black holes to slowly evaporate over enormous timescales, with smaller black holes radiating more quickly than larger ones. This counterintuitive behavior means that stellar mass black holes will actually grow larger over the next trillion years as they absorb cosmic microwave background radiation faster than they can radiate energy away through this quantum process. Binary black holes throughout our galaxy spiral together in gravitational dances that create ripples in space-time itself, sending gravitational waves racing across the universe at light speed. These cosmic tremors stretch and squeeze space by amounts smaller than a proton's width, yet sensitive detectors on Earth can measure these distortions and reconstruct the final moments of black hole mergers occurring millions of light years away. The collision and merger of two stellar mass black holes releases more energy in gravitational waves than all the stars in the observable universe emit in visible light during the same brief period. This staggering energy output occurs not through electromagnetic processes, but through the conversion of orbital energy into gravitational radiation as the two objects spiral inexorably together in their final dance. Intermediate mass black holes may exist in the spaces between stellar mass objects and the supermassive giants that lurk in galactic centers, though confirming their existence remains one of astronomy's greatest challenges. These hypothetical objects could form through the direct collapse of massive gas clouds, or through the growth of primordial black holes that formed in the early universe. But their dark nature makes them extremely difficult to detect unless they actively accrete material. Primordial black holes represent a theoretical population that could have formed during the first fraction of a second after the Big Bang, when quantum fluctuations in density might have created regions compact enough to collapse directly into black holes without first forming stars. If they exist, these ancient objects could comprise some or all of the mysterious dark matter that dominates our galaxy's mass budget. The search for these primordial remnants continues through gravitational microlensing surveys that look for the telltale brightening of background stars as invisible objects pass between them and Earth. Any detection would revolutionize our understanding of both dark matter and the early universe, providing direct evidence of physical processes that occurred before the first atoms formed. Quark stars represent a hypothetical intermediate state between neutron stars and black holes, where the intense pressure at the core breaks down neutrons into their constituent quarks and gluons. These exotic objects might exist in a narrow mass range where neutron degeneracy pressure fails, but gravitational collapse hasn't yet created an event horizon. Strange matter stars could theoretically exist if strange quarks can form stable configurations under extreme conditions, creating objects even denser than neutron stars, but composed of entirely different physics. The surface of such an object would consist of strange matter rather than normal atomic nuclei, creating a boundary between familiar physics and truly alien states of matter. Color glass condensate might exist at the cores of the most massive neutron stars, where matter exists in a state similar to conditions just microseconds after the Big Bang. This exotic phase of matter would consist of densely packed gluons forming a glass-like structure that exhibits both liquid and solid properties simultaneously. The study of compact objects pushes theoretical physics to its limits, requiring the marriage of general relativity, quantum mechanics, and nuclear physics to understand how matter behaves under conditions more extreme than anything achievable in terrestrial laboratories. Each new observation of neutron stars, black holes, and their interactions provides crucial tests of our most fundamental theories about the nature of space, time, and matter. Gravitational wave astronomy has opened an entirely new window on these extreme objects, allowing us to observe black hole mergers, neutron-star collisions, and other violent events that produce no electromagnetic radiation but generate powerful ripples in space-time itself. This revolutionary new field promises to reveal phenomena that remain completely invisible to traditional telescopes. The future detection of gravitational waves from core collapse supernova could provide unprecedented insights into the physics of stellar death and compact object formation, revealing details about neutrino emission, shock wave propagation, and the conditions that determine whether a dying star becomes a neutron star or black hole. Pulsar glitches offer glimpses into the interior structure of neutron stars, where the crystalline crust occasionally cracks under stress and suddenly transfers angular momentum to the fluid core. These starquakes release energies equivalent to magnitude 30 earthquakes, yet they occur on objects smaller than most cities. The equation of state for matter at nuclear densities remains one of the greatest unsolved problems in physics, with implications stretching from neutron star structure to the properties of atomic nuclei. Precise measurements of neutron star masses, radii, and moment of inertia could finally resolve this fundamental question about how matter behaves under extreme conditions. Tidal disruption events occur when ordinary stars venture too close to stellar mass black holes, experiencing gravitational forces so intense that they're stretched beyond their breaking point and torn apart in spectacular displays of cosmic violence. These events create temporary accretion disks that can outshine entire galaxies as stellar material spirals into the black hole. The debris streams from tidally disrupted stars wrap around the black hole in complex orbital configurations, with different portions of the stream returning to the vicinity of the black hole at different times. This creates a characteristic light curve that allows astronomers to study the disruption process and probe the properties of both the black hole and its victim. Hypervelocity stars ejected from binary systems disrupted by stellar mass black holes carry information about these invisible objects encoded in their trajectories and velocities. By tracing these stellar refugees back to their points of origin, astronomers can map the distribution of black holes throughout our galaxy and study the dynamics of close encounters in dense stellar environments. Gamma-ray bursts may originate from the most energetic stellar explosions in our galaxy, occurring when massive stars collapse to form rapidly rotating black holes while simultaneously launching relativistic jets along their rotation axes. These cosmic fireworks release more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. The afterglows of gamma-ray bursts provide laboratories for studying relativistic shock physics, particle acceleration mechanisms, and the propagation of high-energy radiation through the interstellar medium. These events create some of the most extreme physical conditions in the universe outside of black hole event horizons. Superluminous supernovae represent a class of stellar explosions that exceed the energy output of normal core collapse events by factors of 10 or more, possibly involving the formation of rapidly spinning neutron stars with magnetic fields strong enough to power the explosion through electromagnetic energy extraction. Pair instability supernovae could occur when the most massive stars in our galaxy reach core temperatures high enough to convert photons into electron-positron pairs, removing radiation pressure support and triggering catastrophic collapse. These theoretical events would completely destroy the star, leaving no compact remnant behind. The cosmic recycling process continues even after stellar death, as compact objects gradually spiral together under the influence of gravitational wave radiation, eventually merging in cataclysmic events that forge heavy elements through rapid neutron capture processes. These kilonova explosions may be responsible for producing much of the gold, platinum, and uranium found throughout the galaxy. As our journey through the graveyard of stars reveals, death in the cosmos is not an ending, but a transformation, where the fundamental forces of nature sculpt matter into forms so exotic they stretch the boundaries of human comprehension, creating laboratories where the universe experiments with physics at its most extreme limits. The cosmic web that connects our galaxy to the broader universe reveals patterns of breathtaking elegance when viewed on the largest possible scales. Dark matter filaments stretch across hundreds of millions of light years, creating invisible highways along which galaxies flow like beads on cosmic strings. These filaments intersect at massive nodes where galaxy clusters form, creating the largest gravitationally bound structures in the universe. Between these filaments lie vast cosmic voids, regions so empty they contain less than 1/10 the average density of matter found elsewhere in space. Our local group of galaxies rides along one of these dark matter streams, participating in flows that stretch across significant portions of the observable universe. The Great Attractor, a gravitational anomaly located hundreds of millions of light years away, pulls our entire galactic neighborhood toward it at speeds exceeding 600 kilometers per second. Yet even this massive concentration of matter is itself part of an even larger structure, the Shapley supercluster, which exerts its own gravitational influence across even vaster distances. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old, revealing tiny temperature fluctuations that would eventually grow into the cosmic web we observe today. These primordial density variations, amplified by billions of years of gravitational evolution, created the scaffolding upon which all large-scale structure would eventually form. The patterns we see encoded in this ancient light represent the seeds from which galaxies, stars, and ultimately life itself would emerge. Baryon acoustic oscillations frozen into the distribution of galaxies provide a standard ruler for measuring cosmic distances and the expansion history of the universe. These subtle patterns in galaxy clustering represent the fossilized remains of sound waves that propagated through the early universe when it was still hot enough to exist as a plasma. The characteristic scale of these oscillations, imprinted when the universe became transparent to light, provides a fundamental yardstick that astronomers use to map the geometry and evolution of space-time itself. The accelerating expansion of the universe, driven by the mysterious dark energy that comprises 70% of the cosmic energy budget, affects the fate of our galaxy and its neighbors in profound ways. As space continues to expand at an ever-increasing rate, distant galaxy clusters are being carried beyond our cosmic horizon, disappearing forever from our observable universe. Eventually, only the gravitationally bound members of our local group will remain visible, creating an island universe surrounded by an ever-expanding ocean of darkness. The collision between our Milky Way and the Andromeda Galaxy, scheduled to occur in approximately 4 billion years, will unfold against this backdrop of cosmic expansion. As these two spiral giants merge into a single elliptical system, the night sky will be transformed beyond recognition. Stars will be flung into new orbits. Stellar formation will be triggered by gravitational shockwaves, and the supermassive black holes at each galaxy's center will eventually together spiral in a final gravitational wave crescendo that will shake the very fabric of space-time. And now, as we reach the end of our cosmic journey together, I hope you're feeling that same sense of wonder that first drew you to look up at the night sky. We've traveled through 13 billion years of galactic history, explored the births and deaths of countless stars, and discovered that our Milky Way is far more dynamic and mysterious than we ever imagined. From the ancient stellar streams that wrap around us like ghostly ribbons, to the supermassive black hole lurking at our galactic heart. Every fact we've uncovered reveals just how extraordinary our cosmic home truly is. The next time you step outside on a clear night and see that faint band of light stretching across the darkness, remember that you're not just looking at distant stars. You're witnessing the edge of a vast spiral galaxy that contains more wonders than we could explore in 100 lifetimes. You're seeing your address in the universe, written in starlight across the cosmic dark. If this journey through our galactic neighborhood sparked your curiosity or helped you see the night sky with new eyes, consider subscribing for more explorations like this one. Until next time, keep looking up and remember that every breath you take connects you to the stars themselves. Sweet dreams, fellow travelers.